This is the presentation about the practice 2 of petroleum viscoreduction. These are the contents that we are going to talk about in the presentation. First, we have the introduction, second, the methodology, then the results presentation, the discussion and the analysis of results, and finally, the conclusions. The objective of the practice was to analyze the viscoreductive effect of organic solvents in crude oil. In this case, we use a rheometer to measure the viscosity data. What is the problem to solve? Heavy crude oil cannot be transported by pipeline without a previous reduction of its viscosity. In an oil pipeline, crude oil circulates through a pipe thanks to the impulse provided by the pump station. What is the solution to this problem? One of the solutions of the problem is to mix petroleum with light hydrocarbons. What does the resulting viscosity depend on? The resulting viscosity of the mixture depends only on the dilution rate, the respective viscosities and densities of the oil and the diluent. By mixing hydrocarbons and solvents that have polar functional groups in their molecule, it is shown that the dilution efficiency of the heavy crudes increase. At a constant dilution rate, the higher of the parameter polarity of the hydrogen bonding parameter of the solvent, the greater the relative reduction in the viscosity of the diluent crude is. Only polar solvents that have a few hydrogen bonds give a significant reduction in the viscosity of the diluent crude. Where do we get the information from? Viscosity data was obtained using a rheometer. In our case, we use 5% of toluene as organic solvent. The relevance of the petroleum viscoreduction is that the characterization of the viscosity in this type of oils and the study of the behavior in function of the pressure, temperature, amount of dissolvent, density, and chemical composition is essential to validate mobility and therefore establish the optimal exploitation plan that allows the extraction of reserves of hydrocarbons profitable.
In the methodology, first we prepare the mixture of crude oil and toluene. In this step, we used 30 milliliters of oil and added 5% toluene to total volume of petroleum, which were later mixed until the mixture appeared homogeneous. Then we have the viscosity data collection, for which we use a rotational rheometer with a cylindrical coaxial shape. For this, we added 25 milliliters of sample onto the rheometer beaker and lowered the geometry so you get a 5 millimeter gap. Then we selected the method and performed the test with steady state flow, shear range between 1 to 100, 5 steps, and a temperature of 20 degrees Celsius.
Now we will present the results obtained in the lab. Our group had to mix the crude oil with toluene 5% concentration. Okay, so first we have the graph that plots shear stress of crude oil with toluene 5% versus shear rate. The shear stress is measured in pascals and the shear rate is measured in as 1 over seconds. We can see that we have a straight line that represents the behavior of the shear stress as the shear rate increases. Here we have the graph of the viscosity of crude with toluene 5% plotted against shear rate. The viscosity is measured in pascals times second and the shear rate is measured in 1 over second. Here we have to ignore the very steep line at the beginning of the shear rate and just consider the part where it has a negative slope and starts almost at 2.34 Pascal seconds. Now we will compare the results obtained from crude oil without solvent and the crude oil mixed with different solvents, which is the acetone and the toluene. Both of them are at different concentrations, which are 5, 10, and 15%. So first, we graph the shear stress versus shear rate for every solution of the crude with the different solvents. The shear stress is measured in pascals and the shear rate is measured in 1/seconds. We can see that the different mixtures or solutions have different slopes that will be discussed in the analysis section of this presentation. For the viscosity, we first wanted to show the individual viscosity behaviors of the different mixtures. The viscosity is measured in Pascal seconds and the shear rate is measured in 1/seconds. As we can see, they all show similar behaviors, which are decreasing as the shear rate increases, but start at different values. For example, the crude without any solvent starts at 12 Pascal second, and the viscosity of crude with acetone 15% is at 0.3 Pascal seconds. The most important viscosity graph is the one that shows the comparison of every mixture plotted against the shear rate. We can see that they have a slope of 0 almost, and we can see also that the viscosity of the crude oil is very high compared to the mixture of solvents. Now we will proceed to discuss and analyze the results obtained. For this analysis, we will start by looking at the effect of adding a polar solvent to crude oil. We do this mainly to reduce the viscosity of the system. Why this happens? Because the solvent has a dipole-dipole interaction with the polar components that are present in the crude oil. Since we're only looking at the molecular level of the system, we'll take in account the absolute viscosity. This type of viscosity requires the solvent to have as a property a low dipole moment. A low dipole moment is created when there's a difference in the electronegativity of the atoms that are present in the molecule. But the difference with a high dipole moment molecule is that the charges are more balanced. Since the viscosity is directly proportional to the intermolecular forces, when there is a low dipole moment solvent, this means that there is a weaker intermolecular interaction, which can cause a drop in the absolute viscosity. Also, if we increase the concentration of the solvent, this means that there are more molecules per unit of volume of the solvent interacting in the system. As there's more weak interactions, there is interfering with the strong dipole-dipole moment, dipole-dipole interactions in the system. So there is a higher rate reduction in the absolute viscosity. Now we will discuss which of the solvent and concentration is most efficient to use in a real situation. We can see in the graph of viscosity against shear rate that there is a correlation between the type of solvent and concentration with the reduction in the absolute viscosity. So to choose this the best solvent, we can analyze the dipole moments of the solvent. At 20 degrees Celsius, which was the temperature that we got the data in the lab, the dipole moment for toluene is 0.31 and for acetone is 2.69. So we can see that there is a big difference between these dipole moments because toluene is much less than acetone. So we can say that toluene at 15% concentration should be chosen as the most efficient solvent and used in this real life situation of reduction of crude oil viscosity. But the reality is that it's not. Why? Because the reduction in viscosity shown in the single graph of toluene 15% viscosity plotted against shear rate, we can see that the viscosity is around 0.315 Pascal second, which we can convert to centipoise, and it gives us 315 centipoise. To compare, water at 20 degrees Celsius has a viscosity of 1 centipoise. So this means that the crude oil with toluene at 15% is almost 300 times more viscous than water. This can create problems in the transport of crude oil since it's not the viscosity has not reduced as much as we want. So we recommend to increase the concentration of the solvent or change to a solvent with a less value of dipole moment, maybe almost to zero. Now we will discuss the behavior the fluid takes when we add a solvent. According to Ron Darby in his book, if the molecules do exhibit a significant mutual attraction, such as that the force, the shear stress, is proportional to the relative rate of movement, the velocity gradient, the material is known as a Newtonian fluid. We can see in the graph on the left, we have plotted viscosity versus shear rate, the same as we plotted in the result section. The Newtonian fluid is a straight line that has a slope of 0. This is the same result we obtained by every mixture of solvent of acetone and toluene in every single concentration. On the graph on the right, we have the shear stress plotted against shear rate. The Newtonian fluid is a straight line that starts at the origin. This is the same behavior shown in the results section for every single mixture. This is why we can conclude that as for the viscosity and shear stress obtained, we can relate the fluid as a Newtonian fluid behavior.
And finally, conclusions. Our first conclusion is that toluene is the best solvent thanks to its low dipole moment. Then we have that the higher the concentration of the solvent, the lower the viscosity. This is because there will be more molecules interacting with each other and lowering the viscosity. And although the solvents lowered the crude oil's viscosity, a higher concentration of these solvents would yield better results in the vis-breaking process. And finally, we have that one of the limitations of this experiment is that the temperature's effect in the viscosity is neglected, which hinders the accuracy of its results.